In the name of Almighty God, I'm Hassan Kushan, and today I want to talk about classification of orbits, which is subsection of orbits, the chapter of 1.6.2. Let's explore conservation laws in order to learn something about possible orbits of objects in a central force. Now that we have defined the effective potential, we can define the total energy of the orbit, which uh, is equal to T plus V is equal to 1 divided by 2 mr to the power of 2 plus L to the power of 2 divided by 2 mr to the power of 2 plus UR in an equation of 1.38, which is conserved if UR is time dependent. The most interesting part of this formula is the L dependent term in the effective potential, whose 1 divided by r to the power of 2 dependence acts as a centrifugal barrier which imposes an infinite energy cost to get to r is equal to 0 if the body has a non-zero angular momentum. To learn more, let's consider a sample shape for VR as shown in figure 1.13 under the assumption that you are goes to 0 as r goes to infinite, and that the centrifugal term dominates as r goes to 0, meaning that r must have a smaller power over r in the denominator than 1 divided by r to the power of 2, as is the case for gravity, where r is almost equal to 1 divided by r. Two representative orbit energies are marked E1, E2, and E3. An orbit with energy E1 is greater than 0 is unbound. The body comes is from infinity, strikes the centrifugal barrier, and reflects back out to infinity. An orbit with energy E2 is bound and has two turning points with a minimum distance r1 and a maximum distance r2. The body is always stuck between them. That is not to say that the orbit must be periodic. All it means is that for general potential, the body's orbit shape is enclosed within a ring-shaped region bounded by the circles of radius 1 and radius 2. The orbit E3 is a special case where we sit exactly at the minimum of the effective potential. Then there is not enough energy to change the value of R, so the minimum of R corresponds to circular orbits. To find the radius of these orbits, just solve with print R is equal to 0 for R. You should also check for stability by ensuring that V second R is greater than 0. Otherwise, we would be sitting at an unstable maximum. Similarly, for more general orbit energies, we can read off the distance of closest approach by solving E is equal to VR for R. We can be much more specific about orbit shapes in the case UR is equal to co divided by R, as would be the case for gravitational potential. Without getting into the details of the derivation, the results are E is greater than 0, hyperbolic orbit is equal to 0, parabolic orbit, and E is less than 0 is elliptical orbit. As in the more general discussion, since UR falls off at large R and E is less than 0 corresponds to bound orbits, and for a 1 divided by R potential, this happens to take an elliptical shape. For E is equal to V minimum, we have the special case of a circular orbit, which has the lowest possible energy. Now I want to go through the subsection 1.6.3 Kepler's law. Yes, those scare codes are there for a reason. Kepler's three laws are not really laws at all in the sense of Newton's law, which are always true in the context of classical mechanics. Rather, they are three completely logically independent rules of thumb. One of them is almost trivial and totally general, and two of them are far too specific and only approximately true. In any case, here they are in the traditional order. The first rule for Kepler's law is planets move in elliptical orbits with one focus at the sun. The second rule for Kepler's law, planetary orbits sweep out equally areas in equal times. The third law of Kepler's law, if T is the period of a planetary orbit and R is the semi-major axis of the orbit, then T is equal to Ca all to the power of 3 divided by 2, which call the same constant for all planets. Let's start with the first law. The first part is trivial. Planets have bound orbits by definition, as we have seen above. A gravitationally bound orbit is either elliptical or circular, where circular orbit can be considered a limited case of an elliptical orbit where the two foci coincide. The second part is fairly difficult to draw, and strictly speaking, it's not even true. Remember that two bodies orbit about their mutual center of mass. The precise statement is that the Sun and planets both undergo elliptical orbits with a common focus of both ellipses located at their mutual center of mass. The Sun only sits still at the focus under the approximation that is much heavier than any of the planets, such that the reduced mass is nearly equal to the planetary mass. We can even be a little sloppier and say that as long as the central mass of the Sun planet system lies inside the Sun is at the focus throughout its motion. Unfortunately, the GRE has been known to ignore this subtly from time to time, and a question from a 2008 jury suggested that the statement "the Sun is at one focus" is exactly true. Kepler's second law is also known as conservation of areal velocity and means that if you draw vectors from an orbiting planet to the Sun at equal time intervals along the planet's orbit, the orbit would be sliced up into equal area segments. In Figure 1.14, if the two shown portions of the orbit are traversed in equal times, the region marked A and B have equal areas. In fact, this law is completely general for any central potential, not just gravitational force laws. Since it follows immediately from conservation of angular momentum, recall the definition of L. L is equal to m to the power of 2, the partial differentiation of phi based on time, which is included 1 divided by m differentiation of time, which is equal to r to the power of 2 differentiation of phi. The expression on the right hand side is precisely the area element in polar coordinates up to a factor of 2, and L divided by m is constant, so integrating both sides gives us the second law. We are in figure 1.14. Aerial sections illustrating Kepler's second law. The third law is rather tricky to draw, so best to just memorize it. The proportionality between t and all to the power of 3 divided by 2 is exactly 2 for a pure 1 divided by r potential. You probably will not need it, but the proportionality constant chi is divided by 2p divided by the square of g m planet plus m sun. Like the first law, the statement that Chi is the same for all planets is only true in the approximation that Sun is infinitely massive, otherwise the M-planet term is the denominator of Chi matters, and Chi then varies from planet to planet. Thank you so much for watching my tutorial video until the end. And the next chapter we will go to springs and harmonic oscillators.